Everyone, welcome back to Microwave Engineering. For this lecture, I would like to talk a little bit about some of the mathematical intuition behind Maxwell's equations. So to begin, I want to introduce you to a very famous theorem in vector calculus, and it is called the Helmholtz Theorem. Now, you may or may not have been exposed to this very briefly in vector calculus, but it's kind of a fundamental theorem for all of electromagnetic field theory. Basically, I just want you to imagine some vector field f. So it's a function of x, y, and z in 3 dimensions. So at every point in space, there is some vector associated with it. Now, I don't necessarily know what f is. I don't know what that vector field is, but I do know certain bits of information that define the field. So in particular, I have the curl of f, I have the divergence of f, and I know the normal component of f along some closed surface, a closed boundary. So I'm told the curl, the del cross f, is some vector field. I know the divergence is del dot f is some scalar field. And that normal component of f, you see the n hat dot f over some surface f, s. So some arbitrary closed surface is equal to some other value. So if I know these 3 pieces of information, then I am guaranteed a unique solution. I may not know what that solution is, I may not know how to find it, but I do know that there is one and only one solution for f that can simultaneously satisfy all 3 of these conditions. Now, if that feels strange or esoteric to you, then just consider a simple one-dimensional analog to this exact same situation. So for example, I come to you and I say, I'm traveling to the east at 70 miles per hour. And I started my journey from home, presumably some position somewhere, right? And given those 2 bits of information, then you could presumably deduce that my position throughout all time, my x of t, is in fact unique. I haven't necessarily told you how to solve for that function, but you know it exists, and there's only one and only one possible solution that would satisfy these 2 conditions. So in a sense, that's just the Helmholtz equation or Helmholtz theorem in a very simplified one-dimensional version. And if I expand to 3 dimensions with vector fields, then it's just this same idea being extended to that more higher dimensional sense. Okay, so don't think there's anything kind of strange happening here. It's just this notion of I'm telling you derivatives, and if I impose some sort of boundary condition like a starting point, then presumably that means there is a unique solution to my vector field everywhere. And there's nothing particularly strange or mysterious about it. You should have lots of experience with this idea if you've ever taken calculus. So after that, consider Maxwell's equations. We have Faraday's law, Ampere's law, and then 2 forms of Gauss's law. And we're going to focus initially on just the microscopic form of Maxwell's equations, which I've written here for convenience. So we're not going to deal with the idea of material properties just yet. Just look at those equations for what they are. And something interesting should kind of jump out at you in light of the Helmholtz theorem. So you notice if I rearrange Maxwell's equations a little bit, I have 2 vector fields, E and B. So the electric field and the magnetic field. And Maxwell's equations are telling me 2 very important pieces of information about each field. You notice Faraday's law tells me the curl of the electric field, and then Gauss's law tells me the divergence of the electric field. And then Ampere's law is telling me the curl of the magnetic field, and then Gauss's law for magnetism tells me the divergence of the magnetic field. So essentially, Maxwell's equations are telling me the first 2 conditions on the Helmholtz theorem. All I need to do is apply boundary conditions in some sense to generate a unique solution. So in a way, those boundary conditions are for you to decide based on a particular geometry that you're interested in. It could be something simple like just charges and currents wobbling about in free space. There could be some metal boundaries somewhere imposing, an electric field of 0 on different points. Or there could be magnetic materials imposing, slight boundary conditions here and there. Or they could just be in total empty space going out to infinity. Those are all different variations on boundary conditions. And it is up to you, the scientist and mathematician, to decide which boundary conditions are interesting. But all you need are some unique boundary conditions to impose onto those equations in order to create a unique solution. Now, another thing you'll notice is these are not independent equations. So the curl of E is related to B, and then the curl of B is related back to E again. And that's going to have a lot of interesting repercussions, but at the end of the day, the same principle still applies. I have curl, I have divergence, and just because they're intertwined doesn't necessarily change the fact that I know the curl and the divergence, and I just need to impose certain boundary conditions to get a unique solution. And again, I may not know how to calculate that solution. There's a certain art or finesse to it, which we'll delve in later. But that just tells us, given these bits of information, there is a unique solution out there to find. And once you have found that solution, you can rest easy knowing that it is the solution to your particular geometry of interest. So with that in mind, I find it helps to kind of take a step back and ask ourselves, what exactly do E and B represent? Because we have all of this wonderful mathematical formalism that we're going to solve, giving us these nice, amazing field profiles for E and B. But what do they manifest as in our empirical sense experience? So you can think of that as the interpretation of the E and the B field. There's the mathematical formalism, and then what do I have to do at the end of the day to create some kind of measurable result? So I'm going to share with you kind of like at least one classical interpretation. This is ignoring like the quantum mechanical interpretation of photons and quanta per se. We're just looking at kind of the large-scale classical approximation to that quantum effect here. But classically, you can think of the electric and magnetic field as just things that exert forces on charged particles. And the Lorentz force law seems to really encapsulate everything you need to know about that. So you notice there's two contributions to the force law. You have the electric force and then the magnetic force. So the electric force acting on a charge is QE, and then if that charge is moving through a magnetic field, there'll be this other force acting on it, which we manifest as QV cross B. And that to me feels like everything you need to know about what the electric and magnetic field fundamentally do at the end of the day. You have a charged object with some finite mass, and it might be moving through either of these fields. So there can be an electric field and a magnetic field and some motion through them. And there is a net force that will be physically accelerating that particle in accordance with this equation here, the Lorentz force law. Okay, so that is how you tie the mathematics of Maxwell's equations in electric and magnetic fields into something that will manifest as a real measurable thing. And that kind of force acting on things, you can imagine translates to a lot of other measurable properties, such as, for example, current, in a piece of metal, or can even manifest as physical heating of a device as the current dissipates energy ohmically, and these sorts of ideas. So that to me kind of covers everything you need to know about, I guess, sort of like the philosophy of electromagnetism. You have electric fields and magnetic fields, and there's this nice, rich mathematical formalism that you can solve in that pure abstract space. And then there's this kind of interpretation that tells you how those mathematical solutions will manifest as some kind of empirical result given, say, initial conditions and some experimental setup. Okay, so I hope that kind of demystifies Maxwell's equations a bit as we move forward.